Hi, my name is Jin Hwang, and I'm a junior in the Department of Mechanical Engineering here at the University of Michigan. This summer, through the SHORE program, I worked with Professor Donald Siegel on using computer simulations to find novel materials for carbon capture. Now, the motivation for our research comes from the growing rate of carbon emissions from coal-fired power plants. Now, there's currently a growing consensus that greenhouse gas emissions, including carbon dioxide, can cause global climate change. Now, as we can see in this graph in the red-orange, there's currently a rising rate in carbon dioxide emissions from these coal-fired power plants. And as we can see in B, carbon dioxide from fossil fuel use contributes to more than 50% of greenhouse gas emissions. As we can see in graph C, a quarter of that is from the energy supply globally. Now, domestically, 33% of our carbon emissions are from coal-fired power plants, which shows our growing need to control these carbon emissions. Now, the main idea of carbon capture and sequestration is to capture our carbon dioxide emissions from these power plants and sequester them in geological formations. The current state-of-the-art monoethanol amine, or MEA, approach to carbon dioxide is really energy intensive, since you have to break down chemical bonding between these MEAs and carbon dioxide when you want to release them. Now, adsorbents, or physical adsorbents, which physically capture carbon dioxide, can reduce the cost of electricity and for carbon capture. And they're quite efficient and can have high CO2 capacity at a very low cost. Now, metal organic framers can be the solution to our problem. Metal organic framers, or MOFs, are porous materials constructed from metal ions and organic linkers. As you can see in this figure here on the right, MOFs come in various types of formations, and you can kind of think of them as scaffolds with metal linkers between to construct different types of formations, actually. So they have very high surface areas. The current record is over 5,000 meters squared per gram. That's over the surface area of a football field in a gram of this material. They're quite promising materials for gas capture and storage, and there are currently thousands known, which is a huge space to study. Now, for carbon capture, MOFs with open metal sites are key materials for carbon capture at low pressures, since the metal sites interact directly with the carbon dioxide. In a study done by Kaskey and al. At the University of Michigan Chemistry Department, they showed that changing this metal in a MOF, DOBDC, can have dramatic effects on the uptake volume, as you can see in graph D here. When the metal was magnesium, it dramatically increased the uptake volume, and currently magnesium DOBDC is the top MOF for capturing carbon in these flue gas environments. However, it required a significant trial and error experimentation. So the question arises, can we use computation to screen for optimal MOFs for carbon capture? And yes, we can, actually. So we can go through a screening process called virtual high throughput screening, which is basically screening MOFs virtually one after another. Now, the methodology we use here in the Energy Storage and Material Simulation Lab comes from the density functional theory. Now, the DFT, or density functional theory, is an atomistic method based on quantum mechanics. There are no empirical inputs, and is currently used to model electronic structure and predict thermodynamic properties of materials. It's based on an approximation of the Schrodinger's equation shown here, and it's used to basically replicate atomistic behavior and their interactions with other atoms. Now, the objective of our research is to calculate carbon affinities across hundreds of these known and hypothetical MOFs. Now, this is impossible in a single summer, so we did a benchmark case on DOBDC, or MOF 74. Now, as I said before, magnesium DOBDC currently is the best MOF tested under flue gas conditions. Now, we found that there's a correlation between capacity at low pressures and carbon dioxide absorption enthalpy, so we took the approach to compare the enthalpy of magnesium DOBDC to DOBDC of different metal sites and identify possible metal substitutions with strong affinities for carbon dioxide. Now, the results are quite interesting. As you can see in the y-axis, the adsorption enthalpy and the metals listed here with magnesium as the first to the far left, we found 4 possible metal substitutions with a promise for carbon capture, 3 with a higher adsorption enthalpy than magnesium. Now, we can't really disclose the metals for possible patent pending situations. Now, in conclusion, we're currently looking for an efficient, robust material that are needed for carbon capture of flue gas. And MOFs are promising carbon absorbents. They currently set records in capacities and have efficient regeneration. However, the robustness still needs to be studied, and it's quite difficult to identify that best MOF since we still don't really understand the chemistry behind MOF and carbon dioxide attraction, as well as the fact that there's thousands of MOFs out there. Now, virtual high-throughput screening can help identify the optimal MOF for carbon capture and reveal the chemical factors that control the performance of these MOFs. Now, many possibilities are still to be explored. Thank you for listening.